Welcome to the Cosmic Pie Podcast, Episode 18, Season 3. I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
We're broadcasting live here from the campus, University of North Dakota, here in Grand Forks.
Yep.
If you have any questions or comments that you'd like to make throughout the podcast, feel free to use our chat feature that is running. Also, disclaimer, Robert, the last 3 or 4 times seems like I make you do it, so I'll just do it today.
Okay, you do.
Give you a break.
Yeah.
So whatever Robert and I say are just totally our opinions, and not necessarily the opinions of our department, our college, our university, our state government, our federal government, the United Nations, planet Earth, the solar system.
Know. I'll take
the
credit
Milky
for
Way,
planet Earth.
the universe as a whole. How's that? If the universe is teeming with life, there's got to be some life form somewhere that would agree with everything that we say.
Right.
They say that in an infinite universe, and we don't know if we live in one, which is kind of amazing when you think about it.
Right.
That whatever happens here is going to happen guaranteed somewhere else. In fact, it would happen an infinite number of times.
Yep.
So there is like another Robert Moore somewhere.
Sitting here with a Wayne Barkhouse.
More or less.
Yeah. It's crazy, but...
and saying the exact same thing and the same stupid jokes. Maybe they'll get a better laugh.
And other Robert, I am sorry for that.
They'll never know. They're so far away. They'll never receive the signal, you see. So
right.
We're safe forever. We can't influence anybody's decision.
Well, in a universe of infinite possibility, then there's one right next to us, too.
And there's another thing to consider. Time is going to be different.
Yes.
Their time is not going to lapse the same as our time. They could be billions of years
from now
in the future
or
behind.
Yep.
In fact, it makes you wonder, Robert, how would you, let's say you instantly popped out on some random location in the universe at some random time. Is there any way you can think of to determine roughly what time is it?
Part of me wants to say the CMB.
Bingo! And how would you use that?
Well, basically the temperature distribution.
Right on. Exactly. If you can measure the CMB temperature, that will give you an estimate of how long it's been since the beginning of the universe.
Right.
And that would, if it's 3K, then it's roughly the same eon that we live in, right?
Right.
So, yeah, exactly. Very good, Robert. You pass. Well, that's it for today, folks. So, no, just kidding.
Yeah, but the CMB is useful for a lot of things because theoretically you should be able to position orient yourself as well.
Yeah, and you can measure your position relative to the CMB.
Right.
In fact, when the scientists analyze the CMB in detail, one of the things they have to do is remove our motion through those background photons.
Okay.
Because
they'd be blue and red shift.
So you've got to subtract off that contribution. So that gives us an overall measurement of how fast we're moving and in what direction compared to the CMB.
Yep.
So there is that inertial frame, right? But it's that CMB itself is not, at standstill, presumably, right?
Right.
So yeah, you have to.
But somebody even is getting in on the discussion in the chat. What is zero if it's sandwiched between two infinities?
Like that's making me hungry. It's almost supper time here.
Sandwich. Sorry, we got to be a little silly, folks.
Good question. Don't have a good answer, but it's a good question.
It's a good question.
For sure.
We need to have Christopherson back on.
Oh, right. You get into infinity.
Yeah, get the mathematician in here with us.
Okay, Robert, so let's start with looking at some updates in some sense.
Looking at Mars, right?
Yeah, and the update is from the Europa Clipper mission. So remember, this was launched several months ago to go to Jupiter, the Jovian system, and its primary science goal is to investigate Europa.
Hence the name.
Right, and Europa has been an interesting body for many years now because it may be one of those locations where at least deep under the ice shelf, as they would say, if you had a way to drill down, there might be an ocean. Right. And that ocean may contain life at some level.
If you've got liquid water, you've got to wonder. So, I mean, that seems to be the one ubiquitous element to life on Earth.
Isn't Europa, though, the one that we're supposed to stay away from?
It is. So if NASA officials, if you're listening, if you find a black obelisk on Europa, get away.
Before Jupiter turns into a sun, right?
Before Jupiter turns into a sun.
Do you remember that movie? Was it 2010, the second part?
Yep.
And you remember what was happening during that movie? There was a potential war ready to break out between the United States and Russia.
Yes.
It's not so far-fetched today, is it?
It went for a long time. It was far-fetched again. And now it's back to, well, maybe. But we'll see. We do have another question popped up. If we have to subtract our own motion from the CMB, what would Michelson Morley think of that if they were around today?
Yeah, so that's
a good
completely
question.
different because that was based on that pervasive ether
Right.
that would be spread through everywhere, and that light would be the speed of light would depend on the direction.
Right. Whereas with the CMB, our motion simply makes it look hotter or colder.
Yeah, it's no difference than us walking today. It's raining outside, so like us walking through a rainstorm.
Right.
If you run, you're going to get wet, presumably more so in the front part of
Than
you
in the back.
than in the back. It's the same effect.
Yeah.
So
You're going to catch more. Yeah.
yeah,
in
and
the
it has
direction you're
no
going.
impact on the speed of light, obviously.
Right.
Yeah, so that's something different than that. But it's just in general relativity, there's no, absolute frame of reference. And there isn't. The CMB, you can say, this is my speed relative to. You've got to say
CMB.
something. You can't just say, this is my speed.
Right.
Because the first thing somebody would say, relative to what? Right?
Any physicist is going to anyway.
Yeah. I'm traveling at, I don't know, let's say 75 miles per hour.
Relative to what?
Yeah, relative to the highway, because that's the speed limit here on our local interstate, right? Until they raise it to 80 here in a couple of weeks or something, right? So, but yeah, so it always says relative to what? Relative to what? So it's the same kind of thing here. Anyways, the Europa Clipper mission, which will arrive in the Jovian system in April of 2030, which is not that far from now when you think about it. It's about 5 years away.
Mm-hmm.
One of the things it did is it flew by Mars back on March the 1st, within 550 miles. And
Wow,
it's
that's close.
It's close. And it's a good way of getting a situation where you can get real data so you can test your instrument.
Okay.
And that's what you see here is the thermal camera, the thermal imager is being utilized. We have one image that's taken on the left that you see there, sort of black and white grayscale, and then colorized version is on the right. The bright areas are on the order of about 32 Fahrenheit, so 0 Celsius. That's not surprising when you're talking about Mars. And the darker areas, really cold areas, are up to like minus 190 degrees Fahrenheit. Ooh.
And there must be some other artifact effect going on because it's red in the center near the equator where you'd expect, but it gets cooler away from that center. Is that an atmospheric or a line of sight effect?
Yeah, so at these wavelengths, you can see like limb darkening, right? Because you're looking at the edge of the...
Right.
So you're only looking up in the upper atmosphere when you look on the edge.
Okay, so you are looking at a different optical
Yeah,
depth.
so that's an artifact in that sense, right? The
Right.
limb darkening. Just like we see it on the sun. Or
We
other
see it on the
stars.
sun because of our line of sight.
Yes, exactly. And then there are you can see more finer structure on the planet itself that's not due to limb darkening. And then you have the polar caps, which would be on the top.
Yep.
And also you have geological features like, the
Chasms
Olympus Mons and all
Olympus
this
Mons,
kind of
all right.
stuff, right? So that would be
Which-
different.
Olympus Mons probably would be warmer. I hadn't thought about that. But even though it's an active volcano for a long time, it would probably still be some.
Well, you look at
residual
its
heat.
peaks, so they're way above,
Ah, true.
right, quote unquote, sea level or
Yeah.
ground level, as we would have to say for Mars.
It's actually out
So
of
it
the
actually would be
atmosphere
cold,
level.
and it's really up high. I mean, they're higher than Mount Everest.
Yeah.
So that would be extreme. That would be colder for sure on the top. So you do have the geology that you have to worry about. So the thing here is to note is the camera's working. So
Right.
thankfully, you don't want to get all the way to Jupiter and turn on stuff and it doesn't turn on.
And it doesn't turn on, or it turns on and it's buggy. It's not doing what it's supposed to.
So and you got to calibrate this system. And we know what Mars looks like, in a thermal, right? So you can more
Yeah.
easily calculate. In fact, you can take images of Mars from the Earth, right? Like with the Keck telescope using an infrared camera. So you have a way of calibrating the system, which is nice. That's what you
It's
want to
nice.
do.
Yeah. That's a good thing.
And speaking about the Europa Clipper, so the other instrument that it turned on and it took an image of is the one called the ultraviolet spectrograph. And so what you see here is actually a spectrum. You see spectral bins on the bottom. And the red color that you see in that sort of spike in the middle, that red color is actually due to hydrogen in our solar system, which is kind of cool when you think about it. So the spectrograph then is definitely working. And once again, these instruments will be calibrated before the spacecraft reaches Europa.
Now,
in a few years.
I've got to ask because I'm not seeing anything on the axes that orients me because it's talking spectral bin.
Yeah.
What is that referring to? Because that's not wavelength.
No, that's two-dimensional image, spectral image.
Okay.
I mean, like you'd think of integral field unit type of spectrographs, where
Okay.
instead of getting like a one-dimensional spectrum, in this case it's 2 dimensions where every pixel, spaxel as they call them, right, you're getting the spectrum of that pixel.
Okay.
So that's the next generation to go beyond the sort of one-dimensional type of
Okay.
spectrographs.
So
that we
that's
historically used.
definitely something I'll have to read up on
Yeah.
to stay current.
Yeah, so
Because
that's going to be.
I've never even
gonna be
heard of
cool.
that.
In fact, if you get like a spectral image, then IFU image of the surface of Europa, then you can see all the changes on its two-dimensional surface in terms of the changes in the spectrum.
Okay.
And that'll tell you a lot of useful information.
Yeah.
Because the other, how do you do it the other way? Well, you take a line across,
And then
or
a line
you put
across
like
and a line
you know,
across.
or you allow just the light coming into some fiber that's on a specific location, so you get the spectrum of just that single point, and then you have to move it around. It would take forever, the kind of mosaic pattern.
Right.
To take the spectrum of the whole surface of Europa. This way, you do it all in one shot,
Okay.
right? So 2 dimensions. So
Boy,
it is a
that
lot
smacks
better.
of a lot of Fourier transforming. And
But it's worth it.
oh yeah,
It's
I
definitely
agree.
worth it, right? Because that's what you want. Is you want radial spatial changes across the surface to look for different features. So that's going to be really, really interesting.
Absolutely.
Now, speaking about spacecraft that are exploring our solar system,
Are exploring out of it now.
yeah, another update. And this one again, the Voyager 1 spacecraft has been in the news lately. So why it has been in the news is that Voyager 1, of course, needs to send back signals to Earth, and that has to be done by making sure the antenna, the big dish that you see here in this sort of color representation of the Voyager 1 spacecraft, that white dish, that needs to be pointed within, like a small fraction of a degree or so towards the Earth. And so in order to position it correctly, there are onboard thrusters, gas thrusters, that will align the antenna when it's ready to transmit. So the idea is you don't transmit all the time, just once in a while. Periodically you will transmit, but it has to be aligned. In fact, you remember it wasn't that long ago, maybe a year and a half ago.
It misaligned.
Yeah, it misaligned. It took a while to get it back, right?
Yep.
So they were lucky because I think they still received signal from one of the low gain antennas, right? They had a really large side lobe on it and were able to orient itself, fix the problem, and then turn it so that you can run it at the high gain antenna with the bigger bandwidth, right?
And they basically had to redo the EEPROM because several of the circuits on the chip went bad.
Well, if the dish is, let's say, is 90 degrees pointed away from Earth,
You're
done.
You're done.
You're done at that point, right?
Yeah.
And you're never communicated with again. It's over with, right? The computer has to be smart enough if it's running correctly, right? The algorithms to know where it's pointing relative to the background stars, and then it can know where the Earth is, and then realign itself to point towards Earth. And that was the problem it was having in its programming, so it couldn't do that accurately.
Right.
So that was a close call back then. So how they align it was with these thrusters. And what they noticed as these thrusters, according to NASA, then there's some type of residual contamination that's building up in the fuel lines of the thrusters. So,
Interesting.
yeah. So what they did is they took a backup thrusters which weren't working properly, and they made them and they turned them off. This is back in 2004. So like 21 years ago, they turn off these, probably thinking they'll never use them again, right?
Yeah.
So they said, okay, these are done. Let's turn these suckers off. And they've been using this other set, the primary thruster, since then. But they're building up this residual and they're clogging up. Now, the antenna in Australia, so the Deep Space Network, so to communicate with these space probes that are really far away, we usually combine. We have different antennas around the world that we can use. Famous ones like the Goldstone dish in California, the Parkes dish, right, in Australia, and there are other ones over in Europe and so on. And that way, it doesn't matter where the Earth is in terms of its rotation relative to the spacecraft. There's always some antenna that's pointing towards the spacecraft, and you would communicate with that.
Yep.
So this is the Deep Space Network, and NASA has upgraded it over the years to make it more sensitive to space probes that are really far away, like the Voyager and like the Pioneers before they went silent, and so on.
Yep.
And one of the things they're doing is the antenna in Australia is going offline for several months.
Oh, good.
And this means they will not be able to communicate with the spacecraft properly. So they decided, well, because of the problems they're having with the primary thrusters, this may be a good time to see if we can bring up those backup thrusters that we turned off 21 years ago and see if we can get them
running
to be run again so they can act as, take over when these other thrusters are having problems. So you reprogram the computer on board to do that sort of switching. And so they decided to turn on these thrusters. Now, they don't suffer from the clogging that the primary thrusters are suffering from because they haven't been used long enough to build up that residual. They had other problems, which is why they turned them off back that long ago. And so they've changed the coding to go around the problem and actually fixed it, believe it or not. So they actually revived these thrusters. So now they're functioning again.
Nice.
So now we have a true backup that we can switch to, that Voyager 1 will automatically switch to if it detects, a fault in the primary thrusters, even though we're not communicating with the probe, while we do these upgrades.
There you go.
So,
yeah. And that's kind of neat.
Yeah, and just to give you an idea how far away the spacecraft is, so currently it's 167 astronomical units from the sun.
167 times further away than Earth.
Yeah, than the average distance from Earth to the sun. So you think of that, well, how far is that? Think of light travel time. So I decided to put that up there in the bottom. It's 23 hours, 3 minutes, one way.
Right. So it's 2 days to get a signal back.
It's 2 days to get a signal back. So that's amazing when you think about it. Going
That's
to the
a
moon,
long way.
Going to the moon was 2 seconds to get a reply, right? You sent a hi, and then your reply that you receive would come back in about 2 seconds.
Right.
So this is like, 2 days, right? So you're looking at 46 hours and 6 minutes.
Yeah. And I will point out, Pluto, folks, is only 9 light hours away.
Yeah, 80 AU on average.
Right. So this is significantly
double
further
that
away.
distance. Double
So,
that.
But then again, it's been out there traveling for a long time.
Since like 77.
Yeah.
So yeah, it's been a long time. But it's interesting how this technology essentially is 60s technology, right? It takes many years to take the technology, freeze it, do all of the tests and hardening that you do to make sure it's going to survive the space environment, and then put it into the spacecraft itself. So this technology freeze usually happens 5 years or more before the spacecraft is launched.
Right.
So really we're talking about probably late 60s, very early 70s
Technology.
which is interesting from that point of view.
Hi, we're down here in a room off of the math computer lab, by the way, folks. And I was looking at a picture they have on their bulletin board, and it's 1993, and it's these big clunky CRT screens with massive desktop computers on them, and 30 years has made that big a difference, and we're talking 30 years older than that.
Yeah, it's amazing when you think about it.
Oh yeah.
Anyways,
So
yeah, but besides the Voyager and the Europa Clipper mission, there of course are other targets that we can look at in our own solar system, and those targets include, of course,
Titan.
So Titan's is completely cloud covered, at least in the optical, right? The largest moon of Saturn. In fact, it is so large, it is larger than the planet Mercury.
All right.
And it's only second to Ganymede, which is the largest moon in the solar system. And that's one of the moons that was discovered by Galileo back in the early 1600s in orbit around Jupiter.
Well, I like to point out to people that Ganymede and Callisto are large enough and bright enough that if not for the glare of Jupiter, they would be visible on Earth if they were out there by themselves.
Visible on Earth without a telescope
Without
or
a telescope.
binoculars.
Good point. Thank you.
Yeah. So they'd be visible to the unaided eye or the naked eye, as we say.
So, you don't think about Jupiter when you see it in the sky because it looks like just a bright star. What are you talking about? Glare. But it's got enough glare to it, enough disk, that it blocks being able to see Ganymede and Callisto with your eye.
That reminds me, too, for those of you who can't separate the planets from the stars when you look up in the sky and you're wondering, one of the rule of thumbs, if you think that your object you're looking at is a planet, one of the things you'll notice it doesn't twinkle like the other stars around it because it has a disk like. It's not a perfect point source of light.
Right. That said, I have seen Jupiter twinkle.
It will, depending on the atmosphere, for sure.
It was a very windy day, and
in fact, I saw the moon twinkle too, because the clouds pass in and out of it at different densities. So it got brighter and got fainter, got brighter and got fainter.
Yeah, so that can happen too.
Yeah, but we're talking like on a clear night.
But on a clear, calm night, it won't. A planet won't twinkle. Stars still will.
Barely twinkle compared to the stars. Yep. Stars will do a lot more. The twinkling effect.
Anyway, I'm distracting from the view of Titan.
No, that's okay. So one of the goals then of the James Webb Space Telescope, because it operates in the infrared, so it's more easily able to penetrate through the clouds and see the surface features. Mm-hmm. And the follow-up on this is interesting because it ties into the Voyager mission. Voyager 1, its trajectory when it flew by Saturn was such to get it as close as possible. Mm-hmm. And because of that, it did not allow it then to continue on to Uranus and Neptune.
Right.
So the sacrifice was made because we had the Voyager 2 that was coming behind Voyager 1 about like a year later, roughly, that it would go on to Uranus and Neptune, or it could also be made to fly really close to Titan if it was interesting enough. So when Voyager 1 flew by Titan, it was disappointed in the fact that it couldn't see any surface features. The clouds were too thick in the optical.
Right.
It could look at its atmosphere and do some measurement that way, but it wasn't worth sending Voyager 2 on the same sort of path. So it went on the path that took it to Uranus and Neptune.
Right.
Which explains why only one of the Voyager spacecrafts went by those two outer planets. Right. Because of Titan, essentially.
Because we wanted to look at Titan.
Yeah, we wanted to have a better view. And in those days, the telescopes weren't that great, on the ground. Right. And we didn't have adaptive optics or anything like that. That was, proficient as it is today. And we didn't have the Hubble Space Telescope.
Right.
And so we couldn't tell that Titan would be completely cloud covered. Therefore, don't waste Voyager 1. But it happened.
I mean, the biggest ground telescope at that time was still the 200-inch on Mount Palomar, wasn't it?
This has been in the early 80s, yeah. So the 4-meter... Yeah, that's a 5-meter telescope. Yeah, so that's definitely
that was still the biggest one.
Yeah, that was still the biggest one at the time.
The Great Eye, as it was dubbed.
And the adaptive optics really took off in sort of late 1980s. Right. The advancement of computer technology. And so that system really didn't come along to where it is today until the 90s. Mm-hmm. So we didn't have any of that at our disposal. And the Hubble didn't get launched until, 1990. So it wasn't available when they flew by Saturn in, 81.
Right.
And of course, you have to make that course correction at some point, right? You can't wait.
You can't wait till you're
last
there.
moment. Yeah. So there's that you have to worry about. Anyway, so one of the things that's always been intriguing is Titan itself. In fact, the Dragonfly mission is, as we mentioned not that long ago, they're actually constructing and cutting metal.
Yeah.
And that will be like, if you want to call it, like a drone or a helicopter. It'll fly around in different locations on Titan. Titan, thankfully, has an atmosphere, so we can use that to our advantage.
Right.
And one of the things we're going to do is study its features. It's extremely cold, so it's like liquid methane on its surface. It's like a gas station, in that sense, right? But it's extremely cold, and under those bizarre conditions, hydrocarbons around everywhere, that cold environment, and we're going to learn a lot about chemistry and and the interaction with
cryochemistry.
Cryochemistry, yeah, chemistry at very cold temperatures. And so there's like lakes of methane and all that. And we can see that because of the Cassini mission that was in orbit around Saturn before they dumped it in the planet after it was done.
Into Saturn, yeah.
Took nice radar data of Titan itself. And you can see these essentially tributary-like features on its surface. So it's like a running water. But water, of course, at the temperature of Titan, which is like minus 100 and some degrees Fahrenheit, is rock hard. Right? So it's something else that's in liquid form, and that's the methane.
And ethane.
Ethane and these hydrocarbons. So anyway, so it's a very interesting body to study. And so the James Webb had been studying since the time. Yeah.
I'm almost more interested in the chemistry of Titan's atmosphere, though, because there's some strange what we now believe is photochemistry going on there with the UV light that Saturn system does still receive, doing some weird breakdown of those hydrocarbons.
Yeah, so it's going to be interesting, the Dragonfly mission.
Right.
to see what it finds and stuff like that. So not only is the James Webb Space Telescope observing Titan, but even our ground-based telescope, like the Keck telescope, and that's the images you see there on the middle column and the one on the far right. You see different features in the atmosphere and so on. So everybody is kind of got their eye open for Titan.
Yep.
Not surprisingly.
Not surprising. It's the only moon with an atmosphere. How did that happen?
Yeah, it's really, really strange. And under those really bizarre conditions, did life start forming ever?
Ever? Right.
I mean, you'd wonder, right? So if you get a sample of it, don't bring it back to Earth. Don't put it in my backyard.
Don't put that right.
And don't bring it within our biosphere because you never know what it contains until we're 100% sure there's nothing dangerous.
Right.
Yeah. So, so that makes sense. We should have, at some point they will, of course, like, level 5 containment bio space stations
we'll call
in orbit
that
around
level
the Earth.
6 because it's in a space station.
Yeah, okay, we'll call that level 6. Good point.
Yeah.
But that's what we should have, right?
Right, absolutely.
So everything goes through there until they analyze it fully and wait the normal so many days to make sure, that's nothing there that can harm us.
And to me, that's another reason to make these craft at the space station, because then they're bathed in direct UV light from the sun. There's nothing surviving that as far as life on Earth.
Well, that's another reason to have robots doing this work initially.
There you go.
Right? Why would you send a human being when something could happen? You rip your spacesuit and all of a sudden you're contaminated.
Right.
And you don't realize, and then you bring it back to the rest of the crew. And then they bring it back to Earth eventually. You can think of all kinds of horror things. In fact,
several people have.
Think of the Andromeda Strain, right?
Andromeda Strain.
The movies and stuff, right?
Yep.
So yeah, that's going to be interesting to see how they deal with all of that. Now, the life giver, of course, in our solar system is what?
The sun.
The sun. And we know the sun is not rock stable. It goes through spells.
It goes through some temper tantrums, too.
Yes, and we've had several of those. In fact, I guess the last good one was back in last May.
Last May.
When we had that huge display of northern lights. You remember that?
Yep. I remember that well because I had friends down in Louisiana and Georgia that were seeing the aurora.
Now, one of the things we like to do is get a good idea of the different solar activity that the sun does display over time. And one way you want to do this is to get as large as a sort of range of time that you can possibly get to see how things have changed. In fact, we know that shortly, a couple decades after Galileo made observations of the sunspot of the sun, that the sunspots went away.
Right.
And that happened for a long period of time.
75 years?
Yeah,
like so Maunder minimum?
So if Galileo was observing at that time, he wouldn't maybe even notice sunspots.
Mm-hmm.
So, the sun is not, like I said, stable and does the exact same thing that's doing today that it does for thousands of years. So the sun does go through this enhancement of activity. And this latest study is showing evidence for a spike in radiocarbon that was detected here on Earth. And this occurred way back in 12,350 BC. So roughly, 14,000 years ago, there was a spike or increase in solar activity. And that evidence we find here on Earth today.
Right. And how do they find out about this? A large portion for time frames that far back is not tree rings or anything like that. It is the gas that's trapped in these glaciers, like in Greenland or Antarctica. They dig down deep enough, and there's gas bubbles trapped. And in those gas bubbles is essentially a sample of the atmosphere of that time. And so they've gone back and they've looked, and they find an enhanced amount of carbon-14 at about this time frame.
And you rule out anything else that could possibly produce it. And the only thing they can think of that makes sense is that was increased solar activity, charged particles coming from the sun.
Yep, because that's the main source of carbon-14.
Yeah, so it's a good way of using science to trace back into early times and get a better idea of the different change in activity of the sun.
And to me, the scary thing is that if it's done, the sun's done it once, it could do it again. And a blast that size, wow.
I don't think could is even, I think it's too weak of a word. I think it will do it again.
Right.
It's just a matter of when will it happen.
Fair.
Time-wise, temporal-wise. So, Yeah, that's pretty cool when you think about it. Now, you're saying about bubbles trapped in glaciers. We've also used that technique to determine, for example, when rocks. So there's this great push that's been doing for decades now. It's nothing new, where scientists will go on the ice sheets of Antarctica.
Mm-hmm.
So you imagine driving around in a snowmobile or something, looking for rocks on the surface.
Because
Because those rocks shouldn't be there, and the only way those rocks would be there is they probably came from above.
right.
So
they're
meteorites,
probably meteors
rather than
meteorites.
meteorons.
Yeah.
Right? So these are meteorites. And you can take those meteorites then and analyze them in the laboratory. And for some of them, a small number, but for some of them, they noticed that the gas bubbles that get trapped inside of these meteorites that they found, when they analyzed the composition, they were identical to the measurements that we made on the surface of Mars.
Right.
So that's how we can infer that at least for these rocks then that had that identical composition must have came from Mars. They couldn't have originated from the Earth itself somehow or from the moon.
And then when you feed it into mass spectrometry, you find out that the oxygen ratio of oxygen 15, I think, to 16, maybe 14 to 16. Anyway, the ratio is wrong for Earth. And just lots of little things. It gets back to that whole idea that scientists don't like one avenue that says this is what happened. They like different angles that all point to the same thing.
I mean, that was the big controversy back in the 90s when Bill Clinton was president of the United States at the time, where scientists announced that they found possibly life on Mars because the meteorites that were picked up in Antarctica that had gas composition that was identical to what they measured on Mars with the Viking missions.
Right.
They found potential fossils of nanobacteria. Now, since that time, a lot of scientists cast doubt that that's not what they were. They're natural chemical reactions that were occurring.
Yeah.
So I think most scientists are saying no, that wasn't any form of life, but there's a small percentage to hang on to that claim.
Right.
But, I mean, we have to do the detailed analysis of Martian rocks. And that's why it was disappointing in a way when the latest federal budget that's proposed for NASA that came out of the White House,
25% cut.
a complete cut of the Mars sample return mission. Now, to be fair, that mission had really went way, way over budget.
Right.
In fact, under Biden administration, NASA issued a request that entities out there, could you please come up with some plan that would be much cheaper to retrieve samples from Mars? And those samples are being deposited by the Perseverance rover. It's just a matter of going around and collecting them. But of course, that's the hard part. And I don't know what they received back as feedback because I don't think it was fully announced.
Right.
But it didn't seem like anybody was able to come up with a mission that would be able to retrieve those samples and then return them to Earth. That's the hard part. In a reasonable amount of money in terms of budgets are tight.
It's costly to get to Mars in the first place, much less to wander around picking up samples, bringing them back to a launch vehicle, getting off and bringing them back to Earth.
Now, it's interesting to know that China has said that they were going to do that. So the Chinese may be the first people on the Earth that would actually retrieve Martian samples, and maybe they'll beat us to the finding of potential life that exists or still exists on Mars, and they'll make the great discoveries. So it's a trade-off. Do you want to miss this potential greatest discovery in humankind in all the history of history, or do you want to spend the resources and go yourself? I mean, that's a question the society makes all of the time, not just in space exploration, but in many other things as well. Money, 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 money.
It's about money.
That's what it comes down to. Now, also one intriguing place to go to in our solar system.
This is the second planet.
Is the second planet from the sun, the planet Venus. Now, Venus does not have tectonic plates like the Earth, but there is tectonic activity on the surface of Venus because of molten rock, lava flowing under the surface. So there's many, many images taken of volcanoes, extinct volcanoes on the surface. And in fact, if I remember right, it was like a year ago, it was announced that there's like 20,000 volcanoes they detected on the radar images from the Magellan spacecraft back in the 1990s.
And since Venus is about the size of Earth, it should not have cooled down in its interior any more than Earth. So the big question to me is, why aren't there more? Why aren't they still blowing their top?
Yeah. So it's very, very interesting in that point. So here are some examples of some radar scans of the surface taken by the Magellan spacecraft. And that spacecraft is no longer functioning, but it was a radar orbiter spacecraft that went in orbit around Venus, if I remember right, somewhere in the 1990s.
Right.
And did the most detailed radar mapping of the surface of Venus itself. And there are plans, of course, to go back. There's Veritas and Da Vinci, and there are other spacecraft by other nations. In fact, there was a paper that came out last week that said there's about 5 of them that are still in the pipeline that will go, do some detailed exploration of Venus. So radar mapping will get, more higher resolution and stuff,
Right.
and we'll be able to have a better view of what's going on. But you can see here in these 4 separate images, this is evidence for, volcanic activity, and it's the deformation of the surface dropping and rising due to the molten activity
Right.
underneath those areas. If you want to say more about that, Robert.
I would just comment that that's what you're looking for. You don't have plates as mentioned, so you're not going to have as much in the way of transverse motion. But I like pointing out that lower left picture, because to me there's some evidence that there's impact cratering, because there's a few round features with central peaks. But there's all these jagged, nearly parallel line features as well, and circular line features, and those suggest actual crustal movement. And that's what we're looking at for volcanism is these features that generally don't happen. An impact crater is generally concentric, circular in form and everything. And so that and Venus's atmosphere is so much thicker than even Earth's that meteors don't get through it very well.
So why
They do, but
So the Earth and Venus are roughly the same size and mass. Why does the Earth have tectonic plates and Venus doesn't? Is there any idea at all out there that can explain that?
why does Mars not have tectonic plates? Granted, it's a lot smaller, but it's terrestrial, it's rocky. Why doesn't Mercury? And the answer is we don't know. Could I offer a hypothesis? Yes. But I hesitate to do it in case one of my old advisors is listening and
Well, what are they going to do? Reach out and grab
slap
you
me
by
upside
neck
the
or
head.
something?
Yeah.
I mean, think
Okay,
what about here's an analogy: a hard-boiled egg that gets cracked.
Right.
But of course, it needs to be some kind of a mechanism that would cause that cracking. Right? Separation.
That separation, there's something has to be weak jointing, and then something keeps those weak joints. And I believe the answer is what is there present in large quantity on Earth that is not present on Venus or Mars?
Water.
Water. And water is known to lower melting temperatures. It's known to lubricate motion, slippage, and just all of these types of things. And I think, at least in part, the answer is that Earth had a large quantity of liquid water that stayed in the crust and on top of the crust.
So do you need a lot more water underground than what you would have on, let's say, on Earth that didn't have tectonic plates? Is there like an untapped reservoir of water deep underground?
And that is a question of some import that they're still being argued. Now, to clarify, there is no ocean of water underground. There is no ocean of water. But there are minerals that are hydrous, that have water integrated into their molecular and crystal structure. A good one is a mineral we call ringwoodite. And it can be hydrous or anhydrous, with water or without. And so the question is how much, because ringwoodite is ubiquitous in the mantle, but how much water can you trap in hydrous ringwoodite?
So if water acts like a lubricant to allow the slippage, as that's what you're saying, how far down is that lubrication zone?
Bingo. How far down does it go? Because we have from seismic data, check the plates. There's evidence that there's some of these old plates that have been subducted pooling on top of the core at the bottom of the mantle.
Well,
so how did they drag any water down with them? Did they completely dehydrate into the upper mantle? these are why we want to get direct samples of the current magma, the current mantle, because we do have samples of the mantle. They come up in volcanoes like Kilauea. They're called xenoliths, alien rocks.
Right.
And there's also portions of the mantle that are exposed. And
So name me a plate, like Eurasia plate.
Mhm.
That's one. So where is that lubrication occurring? Like how far down is it?
it would be
That's what I'm
occurring.
asking.
It would be occurring at the subduction zones.
So how far down roughly would that be?
And well, I mean, Marianas Trench. It's at the surface.
So it's several miles down, like 10
But
miles down or something?
How far down does it drag the water? That is exactly the question. Because again, it's not liquid water as we think about it. It's not that water is pouring down into the interior of the earth
Right.
and pooling or anything like that.
Right.
But much as your antifreeze works by lowering the freezing point of the water in your radiator, so the water incorporated in these hydrous minerals lowers the melting temperature of those minerals.
And that provides the slippage.
And that
Once
provides
that
some
becomes-
of the slippage, some of the
Yeah,
lubrication. So it's
right.
not that there's a film of water or anything like that. It's just that the water, because the mantle is not molten. But if you lower the temperature, the melting temperature a little bit, then the rocks in that zone become molten.
Are they really molted, or are they just like they deform a lot easier than solid, right?
And now you're thinking like a geologist, sir.
Yeah.
That's exactly the questions that we need to answer and that we want to answer. But, getting down that deep for a physical sniff, if you will, is really challenging.
So people try to drill down, right? There's different. What's the furthest you know that we've drilled down roughly? A couple miles or something?
A couple
10 miles?
Well, no, I don't even think it's that deep. I know we haven't gotten out of the crust.
Yeah.
So, I see people complaining about that. How can we say this about things when we haven't even drilled through the crust yet?
Did you hear the joke about this?
Uh,
There was supposedly, and this is all fake, of course.
yeah.
I don't know, the Soviet Union drilled down in Siberia like
Oh.
miles, and then you heard people down there hollering and screaming
Screaming.
and stuff because
I've heard that.
drilled into hell essentially, right?
And it's like, no, they didn't. They really didn't, folks. But
Makes a good story. Late night radio.
it does. But, how do we know things about what's going on? We know it from seismic data, the wave speed through these materials and everything. We can figure that out. And then we go into the lab. We put together the elements that we know. I mean, the Earth's crust is pretty consistent with its elements. It's potassium, calcium, silicon, oxygen,
Magnesium.
iron.
Right.
We know what the Earth is made out of.
Yeah.
And you put it under you put it in a press, put it under pressure, and heat it up to the appropriate temperature.
Right.
And you can see what these minerals will look like, what they do under those conditions. So I don't have to have a direct sample to still be able to see what's going on. And, as to what kind of pressures can we really achieve. With a diamond anvil cell, so the cells of the press are made out of diamond, we can actually get pressures that are right at the core mantle boundary.
Right.
So, yes, we can make statements about these things.
But to get an in situ type sample,
Would be the
'cause
gold
that's-
standard.
That's where the mystery would come from, right?
Right.
Something surprising you never thought about.
Right,
Then you'd have to explain that, and that might turn everything upside down, how we
right.
view what's actually going on in detail.
Because even with a hydrous mineral, what happens when you squeeze it in a press where you don't have an Earth-sized reservoir?
Yeah, it probably moves out.
It squeezes out.
Yeah.
You got it. So it's fairly tricky to make these hydrous minerals at pressure.
Yeah, because you're doing really small scale type of
There
analysis,
you go.
whatever.
The
survives
higher
in
the
a very
pressure, the
center.
smaller the sample.
Yeah. Okay.
So, These are problems in doing the science, folks.
Yeah, so any planet like this, you'd wonder, how did it come from anyway? Where did it come from to begin
Right.
with? In fact, we even see evidence of planet formation occurring near the center of our own Milky Way galaxy.
And
believe
that
it or
is
not.
phenomenal.
Isn't that neat?
It's
So this data taken with ALMA, which is a sub-millimeter array on top of the Andes Mountains in Chile, and it's looking, and those, essentially it's radio astronomy, but at a very short wavelength.
right.
Looking at structures that when we get a detailed image of them, then we see evidence for the building up of these protoplanetary disks of planets
Right.
in the act of forming around these different stars that we find.
And that's what I find amazing, because as we've discussed here, you've got these polar orbit planets around binaries. You've
Right.
got planets around binaries. You've got planets around the individual stars of the binaries. These are all environments we never thought planets could form, because they're just too dynamic gravitationally.
Right, too harsh of an
Too
environment.
harsh. They should be ripped apart.
Yeah.
And instead, bam, planets. They form everywhere.
That's it. So the physical mechanism to forming a planet must be common everywhere. If it's common everywhere in our own galaxy, it's common in every other galaxy.
Right.
And so the number of planets that exist in the observable universe
Just
is
skyrocketed.
huge.
It's huge.
And like we always say, there's got to be life somewhere else, or it's just an awful waste of space.
Right.
Think of the movie Contact, right? Carl Sagan.
I mean, the number of planets we were talking about, it starts getting into the truly governmental figures.
Right. Yes.
That's a joke, folks.
Picking on that deficit again, right?
Yep.
The debt. And so the other thing, thinking about planet formation, there's an observation that was done recently by the James Webb Space Telescope of a debris disk around the star HD 181327, which is about 155 light years away.
Mm-hmm.
And what they discovered was evidence for water ice.
That's it.
And this is the first time.
Heck yeah.
This is the first time they've seen evidence for this.
I mean, I think we've seen gaseous water.
Yes. We've seen in comets and other stuff, but
Yeah,
not water
but
ice.
not ice. And how do we know that? The spectra tells
Spectrum,
everything.
Yeah. So this is really amazing. So once again, you can use this as evidence that life is, that water
Is everywhere.
is potentially everywhere. It's not just unique to our own solar system or a few other objects that we've looked at beyond.
Right.
It may be everywhere.
And alcohol's everywhere, and amino acids are everywhere, and
Drinks
just
abound.
wow.
Never get thirsty traveling through space. Pretty
Yeah.
cool when you think about it.
I like thinking about it, but as you can probably tell from my voice, I'm getting rather excited about this, because this is stuff that got me interested in all of this.
Now, when we talk about life elsewhere, we don't mean like giraffes.
Oh, heck no.
Right? What we really mean is probably bacteria, microbial type of life is way more abundant than life like you and I.
Right.
That's the kind of stuff.
You and I are a rarity, I believe.
Now,
Sample size of one, though.
sample size of one, but the other thing to think of is that microbes are very hardy,
Right.
right? They put up a fight. They're like us. They want to survive. They want to live.
Right. So how hardy are they?
Well, here's an interesting study that was done recently that is about how clean is the clean rooms at NASA. And it turns out they're not so clean after all.
They should be cleaner than that.
So NASA goes through this whole process of making sure that we do not carry biology anywhere else when we launch something. Okay? So they have these clean rooms. Now, these clean rooms are different levels, to be fair, right? If you're sending a lander to Mars, you want it to be absolutely crystal clear of
Right.
no life forms, no biology, no bacteria, no nothing, right, on that instrument that you're sending into space. What they discovered is that some of these different types of microbes that you see here listed on the right panel, study was recently done, that showed that they actually evolved to resist the clean room environment of NASA.
Decontamination. Yeah.
So they're actually changing their evolution. They're evolving to then resist being killed off. And that's not surprising. How many times we are told by our doctors, right? You take this medicine, you keep taking it until it's gone. Don't take it until you feel better and then throw it away, because you'll have some bacteria, let's say, or a virus that's able to survive and now becomes more robust, more hardy to the medication.
Right.
You have to kill it all, which is why you've got to finish all of your days of taking your medicine, whatever it happens to be.
Yeah. This is why antibiotic resistant bacteria have become a thing, is because we're not taking all our medicine. We are overusing the antibiotics so that these resistant strains become the dominant strain.
Yeah, so then you see this happening here. So it's an interesting study to show that these, bacteria and things can survive and evolve to survive under these really harsh environments.
Do you know what I find most interesting about these resistant bacteria, though? Is if you put them back in normal environments, they are actually less suited to survive.
Yes,
so
'cause
they
they've
will
changed.
die
Yeah.
off under the normal pressure from the normal strain.
Well, it's just like us, right? If you take life forms that existed prior to the great oxidation event that happened here on the Earth, 1.5 billion years ago or something, that those life forms would die out because they're in a super rich oxygen environment now, they would never be able to survive.
For them, they're swimming in poop.
Yeah, and vice versa, right? If
We
you
can't survive in there.
Yes, if you take us and 2 billion years in the past, we'd never be able to survive on Earth.
Right.
Because the oxygen level is just too low.
Right.
It's like 1 or 2% or something like that.
Mm-hmm.
So we never survive.
It's fascinating.
In fact, back before the oxidation event, here's a nice interesting fact. Fires were way less abundant than they are now because there wasn't enough oxygen to support them.
Mm-hmm.
So there can be lightning and stuff.
And it wouldn't cause fires.
Yeah.
Right.
Pretty cool when you think about that.
Absolutely. I mean, and people wonder, how do we know this? Again, it's the chemistry. It's the chemistry of the rocks themselves change depending on the atmosphere.
Yeah.
So
it's really
it's
cool.
neat stuff.
Now, talking about neat stuff, once again, the record has been broken for the most distant galaxy ever observed. So now the new record holder is this one here. It's a galaxy that's at a redshift of 14.44. So this paper was just released not long ago, back on May 16th. And that puts it, if you use like the standard cosmology, that puts it at 279 million years old.
Yeah.
279 million years after the Big Bang.
We just
We're
have
observing this
no
galaxy.
idea how galaxies form.
They have to form super fast. Now, to be fair, this one is just a few million years, couple million years younger than the previous record holder.
But still,
So it's not that huge of a difference. But still, it's another evidence. It's not like there was only one galaxy that ever formed in the whole universe in 300 million years. This is number 2 now
right.
that formed in a little bit less than 300 million years. And there's probably another one out there, and another one, and another one, and another one. We just have to find them.
Right.
They're very faint, hard to see, but with the James Webb Space Telescope,
We're
starting to find them.
And
And you can see the evidence here. So on the figure, it shows you the spectrum of the object itself. So it's basically its brightness as it relates to the wavelength that you observe this object. And you see that huge sort of peak sort of on the left side of center of the bottom figure on the right-hand side. And that's the Lyman alpha line.
right.
So that just normally have 1,216 angstroms.
Nice.
So that's in the ultraviolet. And if that is the line, and the way you tell is, well, if that's Lyman alpha, then the ones that you see labeled there to the right of it, so there's nitrogen,
carbon, helium,
oxygen, and so on, they fall right in the exact spot you expect, and you see, emission lines, you see information there. So it does really seem to be at this redshift, which is amazing when you think about it. So we're finding these really, really distant objects. In fact, we're finding them, eventually we're not going to find any more distant because we have reached the point where we haven't had enough time since the Big Bang for these galaxies to even form. So you're not going to find a galaxy that formed 50 million years after Big Bang because you need more than 50 million years to form a galaxy.
Right.
Clearly, you can form it in 279
79.
million years. But can you form it in 200 million years? Could you form it in 150 million years? We just don't know.
And that just makes me start going more and more. Was this all direct collapse stuff? Was this just matter was dense enough at the time that it just stars formed, period?
Forming these galaxies in direct collapse, you look at something called the free fall time,
Right.
right? You calculate that. So given the size of the galaxy, you could calculate how long would it take something to form if something just collapsed on its own, traveling, at the speed of sound, essentially, right?
Right.
Through gravity. So those will put constraints on your object, presumably. And these galaxies tend to be a low mass. They're not like these super duper
Huge
galaxy
things,
that's
yeah.
10 times the size of the Milky Way or something like that. But
You're the cosmologist, so I'm going to ask you: Could it be that there were still pressure waves in the universe at that time that were had a high enough amplitude, enough energy?
no, in fact, the CMB
Okay.
once again comes in because that was produced. That was visible. It becomes visible to us at 380,000 years.
Right.
So a little over 250,000 years after the Big Bang, and the density fluctuations are very low.
Okay.
So you need
right.
to go from that. That's a direct observation. So you go from that condition, that state of the universe, to what you see now, many, many years later.
Right.
Right? We're talking,
Still talking 200 million years.
You're almost 300 million years
years
later. That's a lot of 380,000 years you can fit in there.
Right.
4 per million years, let's say. So 4 times 3. So you got 1,200 lifetimes of the CMB
Fair.
being released. A lot of things can happen.
Right.
A lot of things can happen.
Still a lot of time in there. It's just a
Yeah, you
lot
don't
less
realize
than
it,
what
but
we
there's
think
still a
we
lot.
thought.
And the thing is, you go back in time, no pun intended, to like several decades ago, let's say 50 years,
Yeah.
when people were talking about galaxy formation, it would take 1 billion years, 2 billion years. Well, where do those numbers come from?
Right.
A lot of that was speculation.
Right.
There
right.
was no hard physical facts
Well,
to say it only takes 1 billion years or only takes 500 million years or whatever. So to be fair, those models, right, that people were using were incomplete. They weren't
Right.
perfect, and they're still not perfect. There's still discrepancies, right?
the same with planet formation. When I was a kid coming up, it was assumed that it took 1 billion years to form a planet. And instead, we're finding out they form in under 100 million years. So the same thing is probably true of galaxies. We thought it took this billion years, and instead, no, it just takes a couple 100 million.
Yeah, you can take your models of galaxy formation, tweak them, and make them form in 300 million years easily.
Right.
But does that mean that that's the way nature followed that plan, that idea, right?
And my statement would be probably not.
Well, you just do the observations, see?
Right.
The observations have to constrain the model, right? Theorists are constrained by experiments.
Yep.
So these observations are new, and they're showing us then that these galaxies formed in a relatively short period of time from what the consensus was, to be fair.
Right.
And that means the models were wrong, right?
And so
they need to be tweaked.
We go back
Because
and
we
retweak
didn't
them.
have any observations. We had observations done many years later,
Mm-hmm.
right? Like observations 14 billion years later, like today, what you see around us, and you go back in time until you get to the most distant galaxy that you ever find, those all constrain those models. But what about prior to that time? And if the most distant galaxy you see is something that released that light 3 billion years or 2 billion years after the Big Bang, then there's like a dark ages in there that you don't
Right.
know what's going on until you make those direct observations.
And that's what JWST is doing for us.
That's the initial design,
There you go.
was to look at the really, really high redshift universe and talk about galaxy formation. So to make discoveries, it's not that unexpected, and it's nothing to do with we got the age of the universe wrong. Instead of 14 billion years old, it's 28 billion. Well, show me something, direct proof that an object is 28 billion years old.
Right.
Where's that proof?
Until then, you're spitballing.
You know, everything is
Everything else says that no, it's
everything we
this
found
age.
so far is younger than 14 billion years,
Yeah.
not older. So where are those very old objects?
Even the CMB.
You know?
You
So that's the thing, right? Your observations have to allow you to guide your models and,
Right.
and your theoretical ideas. Okay, so I think that's it for today. So
Yeah.
we're out of time. Anyways, if you'd like to learn more about these subjects, you want to explore life elsewhere,
Right.
which is really
Or
interesting.
explore how life gets homes to build.
All of these things can be done with higher education, like coming here to UND, taking our classes both on campus and
And
online, and get involved in the different programs, whether in the STEM field or the STEAM field or any other field.
Right.
As long as you keep learning, that's the main thing. In fact, you
Absolutely.
can learn until the end of your life. Hopefully your health stays with you, that you allow you to do that. And, what better way of spending your time on this planet is to learn things.
Absolutely. Absolutely.
Now, our next podcast, which typically would be a week from today, is not going to occur. So we're taking next week off. It is Memorial Day weekend, holiday sort of thing. And so our next podcast will be 2 weeks from today. That would be on June the 3rd.
Okay.
At the same time as 5 p.m. Central Daylight Time. Now, we always leave you with a quote. And Robert, I won't make you guess.
Oh, okay.
For the interest of time. But it's related to life elsewhere.
Okay.
So the quote's actually from Frank Drake.
Oh, okay, Drake.
So this was from 1992. So Frank Drake, for those who don't know, he's what's called the pioneer of the SETI program, the search for extraterrestrial intelligence. And back in, I think, 1960, he did the look for life radio signals coming from another star.
Yeah.
So he kind of pioneered this whole field of using radio telescopes to pick up signals from other intelligent forms of life beyond the Earth.
Right.
And nothing has been found to this date, by the way.
Nope.
But we're still looking, right? Still looking.
It's worthwhile to look.
Yeah, why not? And so here's the quote from Frank Drake. 40 years as an astronomer have not quelled my enthusiasm for laying outside after dark, staring up at the stars. It isn't only the beauty of the night sky that thrills me. It's the sense I have that some of those points of light, which ones I can't even guess, are the homes of stars, of beings not so different from us, daily cares and all, who look across space and wonder just as we do.
Absolutely. Great stuff.
If you haven't already, please give us a thumbs up, subscribe if you haven't subscribed, and thank you very much for watching, and we'll see you in 2 weeks.
See you, folks. Have a good one.